Let's do a simpler volume of revolution example compared to what we did last Friday. Oh, let's take the graph y equals f of x equals square root of x. X going from 0 to 4. And let's just rotate this around the x-axis here. So it's this solid region, two-dimensional region getting rotated around the axis, giving you in the end a three-dimensional solid that is kind of like a horn shape again, but this time it's solid all the way through, you might say. It's like I don't know, a gumdrop on its side or something. You're trying to find the volume of the entire thing. And there's no air in the middle this time, all right? It's a true solid mass, you might say. We're trying to find the volume of that whole thing. The problem-solving process is what's most important. Slice it. And if you are creating a volume of revolution by revolving around a horizontal axis like this, it's definitely simplest to slice perpendicular to that horizontal axis. Maybe your arbitrary thin slice looks about like this. It's not that you couldn't slice perpendicular to the y-axis. You could do that. If you did do that, though, it would be a more complicated kind of problem to solve. You should get the same answer in the end, but it would be more complicated because your cross-sections would not be these thin disks, but instead would be like parabola kind of regions like that. And yeah, that'd be more complicated. So you want to keep things as simple as possible. You use cross-sections, in this case, that are perpendicular to the axis of rotation. Add a certain value of x, call that x right there. And with a certain small width, call it delta x to start with. I will also approach this from the infinitesimal point of view and call it dx2. It's all in how you conceptualize it, whether you want to think of it as just a very small amount of width or an infinitesimal width. I think it's worthwhile to learn both approaches. The small amount of width then gives you a small amount of volume. Delta V, you're imagining to be the small volume of this really thin wafer, right? That doesn't have a hole in it this time. It's not, the cross section is not a ring shape this time. It's just a single circle and its interior. It's a disk, you might say. So the cross-sectional area function that you end up integrating is actually simpler for this kind of problem. You don't have to do pi minus the outer radius squared, or pi times the outer radius squared minus pi times the inner radius squared. It's just pi times the radius squared. That's it. There's just a single radius. But I do ask questions where you sometimes need to write down maybe an approximate equation for this, in this case, volume of the thin slice, volume of the thin chunk, if you like the word chunk. Pretending that the sides are not slanted like you see in the picture, but instead are, in this case, horizontal, so that you're pretending it's a cylinder whose volume would be pi r squared times its height or width. In this case, the width being delta x. Initially, we could write it as the cross-sectional area, A of x, times delta x. But A of x, yes, it is the area of this cross-section. But since that's a disk, a circle, and it's inside, it's pi times the radius squared. But the radius depends on x. So it's good to specify the dependence on x. That's the volume of the thin wafer. The total volume of the entire solid then could be conceptualized as the sum of the volumes of the thin wafers. Being sloppy with our summation sign, not bothering to write I goes from 1 to n. And then replace delta V with what it approximately equals, pi times r of x squared times dx, delta x, excuse me. That's all set up to try to get to the integral. We now let delta x go to 0. Effectively also letting n go to infinity. In the limit as delta x goes to 0, you get the integral of pi times r of x squared over whatever limits of integration you need to get the answer. Looking at the picture, x is varying from 0 up to 4. So you need those as your limits of integration for this problem. Is this a definition or a theorem that you get this? Well, again, if you use the real analysis approach to limits of Riemann sums, which is very general, it's effectively a theorem that you can use the same value, delta x, for each approximating rectangle and let delta x go to 0, that constant value of delta x. So it's really a theorem that gives you the right thing. But it doesn't really matter whether you think of this as a definition or a theorem. It's not magic, though. It only feels like magic. But it's kind of fun to pretend it's magic. It's fun to pretend that the deltas morph into d's and the summation sign morphs into an integral sign. You can maybe even make an animation of those morphings happening just for fun. What's the infinitesimal approach? The infinitesimal approach, or version, I guess I've been calling it, version. Go back up to this equation, that approximate equation, change all the deltas to d's, and change the approximately equal to become an exactly equal to. dv could be thought of as a of x dx. And for a volume of revolution like this, where the cross-section is a disk, a of x is pi times r of x squared. So you could also say dv equals that. And then the total volume is the sum of these infinitesimal volumes. You imagine the integral sign as meaning sum. Just an imagination tool, a convenient fiction. Then you say, hey, I actually have to do the integral, so I better get it in terms of x, and I better have limits of integration. So then you just write your final definite integral to do. You don't bother saying let dx go to 0. You don't bother writing a summation sign. Instead, you write an integral sign there. But you do want an integral in the end, a definite integral that can actually be done. It's done this kind of way all the time in science textbooks. So that's why I'm trying to teach you about it, but I'm trying to also emphasize it's not rigorous math. It's intuitive, fun, conceptual, fiction math to try to get answers, and also, yeah, to try to develop intuition. And I'm going to continue emphasizing it throughout chapter 8. Probably the biggest downside, well, with really either of these approaches, is when you don't have much experience, there's always this gnawing feeling in your gut, like, am I really doing this right or not? And to tell you the truth, in more complicated situations, I sometimes have that feeling too. Am I really doing it right or not? You have to sort of try examples as well to get some internal feedback about whether it seems right or not, especially in more complicated situations that you can encounter, for example, in a mechanics class or an electricity and magnetism class, those kinds of things. For our example, r of x is the square root of x. Why? Look at the cross-section. There's r in the cross-section right here. What does that correspond to in this picture? It's a bit messy, but let me try to make it in green. The vertical distance between the x-axis and the curve is r of x right there. That's r of x. And since you're rotating around the x-axis where y is 0, r of x just equals f of x. Square root of x. It's the same thing. R of x, for this example, does equal square root of x. So you actually end up with a pretty easy integral to do. You get pi over 2 x squared evaluated from 0 to 4. 4 squared 16. 16 divided by 2 is 8. 8 pi would be the answer, which is in the ballpark of 25 or so. If the units of length were, say, centimeters, then the units of this would be cubic centimeters. If the units of length were meters, this would be cubic meters. Is this a reasonable answer? Something close to 25? Well, if you may put this in a box, a 3D box, I'm not trying to draw it somewhat here, of side lengths 4, 4, and 4, the volume of that box would be 4 cubed, 64. Our volume is certainly less than 64. If this were a true cone, if these sides were straight, the volume would be 64 divided by 3, 21 1/3, I think. It's a little bit thicker than a plain old cone, and so you should expect a volume a bit bigger than 21 1/3. Yeah, that's close to 25. Seems reasonable.